Okay, so this is, we're looking at exam number 2, and for Engineering Science 2143, this is our sample exam. It's from 2012 fall. You have access to the PDF and the solutions to this exam in your module, but I'm just going to work the problem out for you. So I want to determine the displacement of point D on the axially loaded system. The members are made of aluminum, A36 steel, and unobtainium. The members are square in cross-section, that's important, square in cross-section, with dimensions shown. The supported A is fixed. Provide your answer to 3 digits beyond the decimal. Okay, so I want to find the displacement of D. So if I want the displacement of D with respect to A, it's going to be the displacement of A to B plus the displacement of B to C plus the displacement of C to D. Okay, and I am given all of these loadings. So I have to find the internal forces. I need to find what is the internal, because I know that delta, if we have stress equals E times strain, okay, stress is just that internal normal force over cross-sectional area equals E times, well, what is strain? Change in length over original length. So I can rework this, and I know that delta equals NL over AE. So I'm given original lengths of everything, that's given. Cross-sectionals, I'm given a 3-inch square, a 1-inch square, a 2-inch square, so I have 9 inches squared, 1 inches squared, and 4 inches squared. And E, I can go back to my equation sheet, and I should have E for all of these. So what I need to find is that internal N, so that I can calculate delta, so that I can add it all up. So let's start with a free body diagram. And if I'm pushing here at 5 kips, I could call this positive NCD, and I could sum forces in the X direction, and I'm going to find that NCD is negative. So visually, I can go ahead and look at this. Okay, visually, I can go ahead and see that I'm going to be in compression, that my normal force from C to D is equal to 5 kips. It's also in compression, which is important because if I have compression, it's going to be actually a negative value. I guess it wouldn't be there. It's the C to D. That's going to be negative because we're in compression. Okay, so we're going to leave it as positive up here, but I just want you to be very, very aware that it's actually in compression. And now I need to, okay, take my Post-it note. That's how I drew that one. Take my Post-it note, and now I'm going to be drawing a longer free body diagram, and I'm cutting it here. So I have an internal that's from B to C, okay, and I have 5 kips that's pushing, and I have 30 kips in this direction, and they're symmetric, so they aren't creating a moment. We can just add them up through the centroid. And so when I look at this visually, I can see that we are going to be 25 kips, and we are in tension. Okay, now I can cut here, and I'm going to draw the world's largest free body diagram. I have 5 kips, I have 30 kips, and I have 60 kips. So I'm looking at 65 in this direction, 30 in that direction, so I can see that we are going to have to be pushing back. My normal from A to B is 35 kips, and it's in compression. So if you need to assume it positive in tension, do your equilibrium, find that it's negative, realize it's in compression, and pushing back in. So now if I want, I can draw a normal force diagram between all of these. And this is my normal force. It is in units of kips. And we are compression at the bottom. We are tension at the top. So I have a negative 35. And then I have 25 kips in tension. 25. And then I have negative 5 in compression. Okay. So now we need to determine the change in length of each of these sections, and we've already come up with the equation that delta equals PL over AE. So the first thing we need to make sure is we have to make sure we're in the elastic region, because we can only use this if we're in the elastic region. Otherwise, we have to go to a stress strain chart. So let's just calculate the stress here from A to B. So the stress here is normal over area. So we have negative 35 kips divided by 9 inches squared. And when I do this, I'm going to get that my stress from A to B is a negative 3.89 KSI. And if I go back and look at my chart, I'm going to see that for the aluminum, my yield is 60. Okay, so we can definitely see that this is less than 60 KSI. So we are in the elastic region. Okay, stress equals 25 kips over cross section 1 by 1 is 1 inch squared. So our stress is 25 KSI. Steel, we know that yield is 36 KSI. So we are definitely in the elastic region. Perfect. I love it when we're in the elastic region. Again, stress from C to D equals that internal normal, 5 kips. Divided by 2 times 2 is 4 inches squared. So I get negative 1.25 inches KSI. And if I go back and look at my equation sheet, which I'll pull that back up, so that's why it's important to know, where am I coming up with these numbers? Well, here's your equation sheet, okay? Here's my yield for aluminum. Here's my yield for steel. And here is my yield here of 5 KSI. So we can see that this 1.25 is less than yield of 5 KSI. So we are in elastic all the way across. If I could put a clapping hands emoji on here, here would be my clapping hands. They actually look like fire, but yay, I can just use delta equals PL over AE. So let's just continue underneath here. So delta equals, okay, my force, my P, that force is actually a negative 35 kips because it's in compression, so it's negative. My original length is 10 inches. Okay, my area again is that 9 inches squared, and E, if I go back and look on my sheet, okay, that's why you guys are given these, you're given these sheets. I can go back and look at E is given at 10,600 KSI. 10,600 KSI. And this is from A to B. Okay. My delta from B to C is, we're in tension, so a positive 25 kips. Its original length is 8 inches. Its cross-sectional area is 1 inch squared. And it has a modulus of elasticity of 29,000 KSI. And again, this one's positive. Now we come over here and we're going to find delta of C to D. It is in compression, so we have negative 5 kips. Okay, its original length is given at 12 inches. So let's 12 inches. Area, our area is 4 inches squared. And its value of E is given as 4,650 KSI. So our units are working out perfect. We have kips and inches, KSI, kips, inches, KSI. And now I can just solve those equations. Okay, I can solve those equations. And I'm going to get that delta of D with respect to A is going to be negative, okay, 3.67 times 10 to the negative 2 inches plus 6.8965 times 10 to the negative 3, okay, minus 3.2258 times 10 to the negative third. These are all in inches. So the displacement is going to be 1.98 times 10 to the negative 6 inches. Okay, that's what we do. Just make sure you're keeping track of compression and you're keeping track of tension. And then you can get that final change in length. And I've got appropriate units. So easy peasy.